All right, in chapter 14, we're going to take a look at antimicrobial drugs. And this will include antibiotics, but also drugs that are purposed for other microbial infections. And before we get started, I just kind of want to give you a little bit of a pep talk. This is just an introduction to antimicrobial drugs. Depending on what health program you progress into, you will definitely have layered instruction on pharmacology and the pathophysiology behind all of these diseases and all of these drugs. But I just kind of want to give you some familiarity with general classes of drugs and really make a distinction between, how antibiotics work and other antimicrobial drugs are functioning in the body. So first, let's kind of look at the history a little bit. And what is so impressive to me is that antibiotics really are not that old. Like when you look at the history of medicine, we've really only had these drugs for about 80 years. Now, penicillin is kind of like the gold star. It was one of the original, antibiotics that were discovered. But it really wasn't until the 40s when the United States Army really started to manufacture penicillin and make it clinically available that it transformed the prognosis of anybody who had a major trauma, surgery, or even a bacterial infection. So just think about that. Think about the fact that we've only had these drugs for a short time. They've completely, radically changed everything about medicine. I mean, imagine having a surgery where they, try to have all these sterile techniques and everything, but, you open up your body to air, there's gonna be microbes in the air. I don't care how perfect sterile processing everything is. It's just, this is sort of like your last defense. Anyway, I will say, kind of some cool history here. They were tinkering with different chemicals, different drugs. Penicillin, I think, is actually kind of the most interesting historically because it was an accidental discovery where basically Alexander Fleming had bad aseptic technique, got a little mold on his petri dish. That happens all the time. But instead of throwing it away, he was like, this mold seems to be inhibiting the bacterial colonies that he was actually interested in. And rather than tossing it, he's like, I wonder what that is. Like, I wonder if I can harness that chemical. I wonder if that can be a useful therapeutic agent. And then, game on from that point on. And, they used to just give penicillin to everybody, everything under the sun. Now we really understand a little bit better about how penicillin works, so we don't just, give it for every type of infection. But certainly, game changer. All right, a couple other terms that we're going to be using in this chapter. Chemotherapy. I know that word makes you automatically think of like cancer. And, it is a cancer treatment. But chemotherapy is actually more general. It just means a chemical drug used as a therapeutic agent. Even Tylenol is a chemotherapy. Like pretty much anything that is a chemical substance that you'd put into your body would qualify as a chemotherapy. So if it's a drug, that's a word we're going to use. Now, antimicrobial drugs are specifically going to interfere with some kind of microbe. Could mess up their metabolism, it could attach to their flagella, might break apart their, DNA or RNA or something, but it's definitely engineered to have an effect on a microbial level. Now, antibiotics are a little bit different. Antibiotics are actually substances produced by microbes. Now, these could be produced by bacteria or a fungus or other types of microbes, but these are just naturally occurring substances in microbes that they use to have some sort of competitive advantage. They're in constant competition with one another for food, for resources, for space. It makes sense that we look to them for the inspiration of drugs that might actually give us an advantage against specific microbes. That's kind of cool. We're using nature against nature. Now, I will also point out that a lot of antibiotics are taken into a laboratory and modified. They are made more clinically efficacious. They are more potent. They have less side effects. That's great, which means we don't like squeeze a bacteria to try to get, penicillin anymore. We're definitely harnessing these in the biochemistry lab. Another term associated with antibiotics is the spectrum of activity. And the broader the spectrum of activity, the bigger the range of microbes that chemotherapy is going to be effective against. So, a broader spectrum antibiotic maybe it affects gram-positive and gram-negative bacteria. A narrow spectrum of activity would be maybe just gram-negative bacteria, or maybe even a genus of bacteria. It could get even more narrow than that. Something else to consider with any drug is selective toxicity. And unfortunately, that is a concern that we have. Some drugs cause a lot of side effects, and sometimes you just have to survive the side effects a little bit better than the infectious microbes that you're trying to kill. But that's always a concern. We always have to measure, how is this interfering with your gut's microbiome? Or maybe does this harm your own mitochondria or other cellular damage? That's always a concern. Now, in terms of antibiotics, which are kind of where we're going to start here, I want you to keep in mind that they can have a range of differences that start from maybe where they were isolated from. Was it from a fungus? Was it from a bacteria? Was it from something engineered in a lab? Who knows? What's their chemical structure? One of the cool things about antibiotics is that sometimes they have these very predictable chemical structures, like rings and side groups, and that's kind of cool. Allows us to sort of study how those molecules actually work in our body. Their chemotherapeutic index, where do they actually work in your body? How does that happen? That is all stuff we need to study. Do they kill bacteria, or do they just stop them from reproducing? Those are two very different actions, really important to consider. Their spectrum of activity, like I mentioned, are they broad or narrow? Do they kill all bacteria, or is it just targeting maybe E. coli? Pharmacokinetics, that's kind of like when you have this drug in your body, how does it concentrate? How does it circulate? Is it moving in the blood? Is it moving in the GI tract? Does your kidneys break it down? How often do you have to take another dose because your body has actually cleared it out of its systems? Those are kind of interesting things. Some antibiotics you take once a day, some once a week, some by IV, some by mouth. It really depends. Their site of action is going to be super important. That is, how does it attack a microbe? Does it attack the cell wall? Does it attack the inner lipid membrane? Does it attack genetic material? We have drugs for all of those different features of microbes. Does it interact with other agents? This is actually really important. A lot of times when people are sick, they're on more than one medication. Does this antibiotic get stronger or weaker with different chemicals? And these can actually even be food. Grapefruit juice is a pretty good example of something that can actually make a lot of drugs toxic. It's so weird to me because it's really just, it's like a fruit, right? But that makes it really complicated when you're trying to do all the pharmacology of all of these potential interactions. Perhaps the most important point for me in this class is going to be the potential for resistance. When we use these drugs, keep in mind that they're naturally occurring compounds that these microbes have developed for their own warfare. If that is the case, they will just evolve new strategies amongst one another. They're designed to have relaxation of proofreading mechanisms, and they allow for mutations and variations to occur when they are under stress, which is when they're, competing with one another. That means, of course, microbes are going to develop resistance. If we overuse these chemicals, they will no longer be of any medicinal value to us because the microbes will just kind of evolve ways against them. And I gotta tell you, I know COVID is still sort of a big deal. There's a lot of other medical kind of problems that we're dealing with after the rattle to our system. But microbial resistance and our lack of new antibiotic drugs is going to be one of the bigger problems in the short term for us. Like, we're just kind of running out of options. Toxicity, as I mentioned, is always a concern. We want to be as toxic to the microbe as possible with the least toxic side effects to the host, which is us. And I will just kind of put this out there. I know it's controversial, but I do think the cost matters. A lot of people want really cheap drugs. This is kind of a dilemma that we have. Are antibiotics too available? Are they too cheap? Are we just like giving them away for free? Maybe they should be more special. Maybe we should reserve them for, the big guns kind of conversations. Anyway, that's something just kind of consider when we think about this problem of resistance. All right, here's just a general textbook picture of all the things you can target with drugs. We can see the plasma membrane can be a target with a bunch of different drugs. Some of these are going to look familiar in a minute. Polymyxins are one of the drugs in Neosporin. So like an antibiotic triple ointment, that's one of the targets. We will see cell wall classic attack action. This would be, the old but true penicillin, but also bacitracin, which is a topical staph infection treatment, kind of your first line of a staph infection treatment. But clearly, since cell walls have the peptidoglycan, and that's kind of a special substance in microbes, that's a really great target, because we don't actually have peptidoglycan, so selective toxicity there would be great. Super advantageous for us. We have some drugs that are going to attack DNA or RNA synthesis. These are pretty hardcore antibiotics, things like Cipro. I will say for certain types of really hard to treat infections like urinary tract infections, that can be a route of our approach. Metabolic pathway, like disruptors, I would say. If we kind of understand how microbes metabolize certain things, especially if they're special and specific to microbial metabolism, if we can find some kind of molecule to get into a protein and really gum it up, that can be effective. We can also work on drugs that attach or attack or disable ribosomes or the whole transcription translation pathway. I don't know. I will just say that we have drugs for just about every little part of a bacteria. Let's start with the cell wall inhibitors. Now, penicillin is probably the best example. We've talked about it before. Also, some newer generations of drugs like the cephalosporins, the monobactams, they all have a very similar chemical structure. And I don't want you to memorize that chemical structure, but I want you to appreciate that they all are very similar looking biochemically. So let's just kind of take a look at this. I know this is kind of hard, a little bit of organic chemistry here, but look at some of these central square-like configurations of molecules. And then we have these side rings. What you'll notice about these drugs is even though they're very different, they might have a different way of being administered. Maybe some are through IV, some are oral, maybe some are injected. They kind of have a similar chemical nature. And one of the nice things about biochemistry of antimicrobial drugs is we don't have to start from scratch. When we're looking at a new drug or a new chemical compound, sometimes we can just start with what we know and tweak those little side groups and give it maybe a special enhancement that gives it more of a broader or narrow spectrum of activity, less toxicity, something like that. Anyway, it's just kind of cool that all the cell wall inhibitor drugs have sort of this common structure. One of the most important cell wall structure attacking drugs will be for MRSA. MRSA, I have mentioned it before, is a methicillin resistant, methicillin is just a type of antibiotic, methicillin resistant Staph aureus. So this is a gram-positive staphylococci. Staph that is in this group tends to be invasive, which means it gets inside a pore or maybe even a puncture wound, a surgical procedure. If it gets past your skin's defenses, there's really not a lot stopping it from becoming flesh-eating like bacteria. And these are two really horrific examples. This was actually a knee replacement, and this is another surgical procedure that got infected. This is terrible stuff, right? And we have to approach MRSA with drugs that actually attack the cell wall, because it has such a gram-positive thick cell wall, tends to be its biggest vulnerability. I will just say IV vancomycin is really our last resort for systemic infections. And remember, systemic infection is where it crosses into the bloodstream and then it can circulate to all the body's organ systems, and that can be fatal in a very short period of time. Protein synthesis inhibitor. So here's basically the whole ribosome like assembly manufacturing system for translation. So we have our messenger RNA, we have a small and a larger ribosomal subunit, we have transfer RNA. This is basically the whole biology 112, protein synthesis kind of topic. I don't want to dwell on the steps here, but what I want to say is we have drugs that will interfere with almost every one of these steps. We have some that will attack the smaller unit of the ribosome, some the larger unit of the ribosome, some the transfer RNA. Basically, this is a great, complicated process to mess up. And some of these drugs are actually very significant. I will mention tetracycline as one that is very common. Tetracycline is a really broad spectrum drug. It's often used for treatment of acne, or there's some other reasons you might have heard of tetracycline, but it tends to have a really broad spectrum in this class, just because every microbe has protein synthesis happening all the time. For metabolic pathway inhibitors, I just want you to sort of visualize enzymes having an active site. A lot of these drugs work by mimicking the shape of the molecule that fits into that active binding site. And once it's stuck in there, it's stuck, and that enzyme is basically taken offline. These can be really effective. The problem is you just have to find these things. You have to find the right metabolic pathway inhibitor for a specific microbe. They can have a more narrow spectrum of activity, which is good because, like, if we want to target a really specific thing but not disrupt, every microbe in the body, it just takes a lot of trial and error, I would say. Let's kind of move away from antibacterial drugs and talk a little bit about antifungal drugs for a second. Remember, a fungus is a eukaryote, and because it is a eukaryote, it is going to have a lot more similarity to you, which means a lot of antifungal therapies have side effects. They can have toxic dose, and they don't always work very well because, of course, we have to protect the host. So I will say some of these are derivative of cholesterol, and they kind of have a chemistry that gives you a vibe of the cholesterol ring structure. But I think the most important thing about antifungal drugs is that they're complicated. Sometimes we don't really understand how they work specifically. We'll just know that they do have some kind of an effect based on observational studies. But I'll kind of just tell you there's a lot of little superficial funguses, like, athlete's foot is a good example. Athlete's foot is really hard to treat, takes a lot of dose, takes a long course of therapy, and sometimes the outcomes are not ideal. Sometimes it just doesn't go away. And there is some debate in medicine if we should maybe allow certain small things to, exist, rather than try to throw a bunch of research and, billions of dollars in drug development at something that's more of a nuisance than a life-threatening sort of problem. Now, there are side effects to consider always. Maybe the foot fungus is a trade-off, like a little itchy toe, a little peely skin, that kind of stuff. Just some food for thought. Antiprotozoan drugs, and this little guy is Giardia. It looks like he has little eyeballs, but those are actually just little dense bodies, but kind of a cool little parasite. A lot of protozoa are going to come from untreated water or soil contamination, those types of things. I will tell you, it can be very difficult to treat protozoa, just like a fungal infection. Chloroquine is kind of a classic example of an antiprotozoan drugs. Chloroquine, super old chemotherapy for treating malaria. Interesting little fact, tonic water has a small amount of chloroquine in it. And if you kind of taste tonic water, to me, it has almost a metallic taste to it. They used to recommend a gin and tonic as a safari, prophylaxis for not catching malaria. And there was actually some evidence to support that could be a good approach. But chloroquine can sort of be in some antimalarials now, but we don't use it by itself because malaria can be developing resistance. We kind of throw malaria treatment with a variety of drugs at once. Diiodohydroxyquine. There's some amoebas that we use for that. Metronidazole. There's some other sort of protozoa that we'll see have either a unknown action or a specific action targeting DNA. Usually that's kind of what we go for with protozoa. But let me just tell you, a lot of antiprotozoan treatments do have a lot of side effects. Those can be a range from blindness to nightmares to just GI disturbances and that kind of stuff. But it can be a hard choice for people if blindness is a potential side effect of taking prophylactic antiprotozoan drugs. Anti-helminth drugs. Now remember, worms are even worse because now we're talking about animals that are basically infecting and eating our body's tissues. Lots of different types of helminths out there: tapeworms, flatworms, roundworms. Good news, most people do not have worms in the United States. It's more of a tropical malady at this point. But we do, of course, have people who travel and come back or maybe even immigrate from places. They need to have treatments available. We have drugs that will target pretty much the metabolic outputs of these worms, I guess. I will say it would be ideal if we had anti-helminth therapy that killed and removed the worms, but that is not actually the case. If you look at this list, we can deprive them of energy, we can paralyze them, we can starve them. We really don't have a good worm eradication drug, and it is because of the selective toxicity issue. If it's going to affect a worm, it's probably going to affect you. So that's unfortunate. I would just say better not to get the worms ingested in the first place. They can usually be ingested. A lot of times, maybe avoid ripe fruit or undercooked meat or dairy products. And sometimes worms can actually burrow in through the skin. So that can be a problem too, like swimming or walking barefoot, that kind of thing. Antiviral drugs, I've mentioned acyclovir before. This is going to disrupt viral replication. This can be a very effective antiviral remedy for very specific types of viral infections. This is particularly useful for herpes viruses, and herpes can range from anything from cold sores to shingles. So there's lots of viruses in that group. It can be a very effective strategy for mitigating the intensity of a viral outbreak, but also some people will take maybe an acyclovir a day to suppress their body's outbreaks from happening in the first place, which is kind of cool. I wish we had antiviral drugs for everything, but it really sort of depends on the virus and how fast that virus can evolve. Okay, so some bigger philosophical things that I want you to think of. First, drug resistance, and this is especially important for antibiotics. And I kind of want you to think about the drug resistance in terms of that video, because you really don't see the impact of drug resistance until you see it kill people. It actually is now, we're living in a time when a scratch on the playground can lead to a life-threatening organ failure. And it's not a joke. This is going to kill probably more people than maybe anything else in the near future. And I want you to know that microbes have mechanisms of creating antibiotic resistance. It's just like they're evolving quickly to keep up with one another. As soon as one microbe creates a new weapon, for the others to survive, they have to have a defensive strategy. And that means they have to be able to evade it. They can either destroy it with an enzyme. They can create a shell or a capsule or a slime layer that means the drug can't get in. They can alter the drug's target site so it doesn't work anymore. Or maybe they can spit it back out. They can do all sorts of things. But the fact is, they're going to find a strategy to survive. I will also say something very interesting to me is that resistance genes are something that they often share amongst themselves. And this is not species specific. What we see is that pathogenic bacteria that can resist a certain chemical will freely give it away to other species. And then those other species are like, whoa, this is cool. I'm going to keep it. And then I'm going to be resistant to that. I'm going to have resistance to that forever too, which is terrifying, really terrifying. I will also say that they don't have to just transfer it via a pilus. When a microbe disintegrates or dies, some of that DNA can actually be slurped up by other bacteria, and then they just keep it there and then use it for their own, like, finders keepers kinds of businesses. So I will say, we know they have this ability. We have to take this into consideration when we use drugs, that they have a limited lifespan. It's just going to be the fact that these things are going to want to survive. So that leads us to our next question, which is, how can we prevent this from happening? Well, one way we can prevent this from happening is by not misusing antibiotics. And I will say it's good to know that there is a way we can maybe reduce our use of antibiotics. I just have a couple suggestions about this. There's going to be some other ideas that you have, which I think is great. But just to kind of get started of things we could do that are easy. We could not keep drugs that we didn't take, keep them in the, medicine cabinet or wherever you keep your old pill bottles, and maybe save them for a rainy day, because, it is a pain in the butt to go to the doctor and you're like, oh, well, maybe if I have another, outbreak of acne or something, I'll just use some of those old ones. You should know that antibiotics are light sensitive and they lose their efficacy with time and exposure to light. So if you're taking a drug that's only 80% effective, 20% of the bacteria, the strongest 20%, are going to not be impacted. And then you have a super strong population kind of starting over, which is way worse. This is another one that I think we all need to take in mind, really into heart, right? And that is to not use antibiotics for something that's not a bacterial infection. Now, a lot of times, doctors are like, well, just in case, I don't want to miss something. I don't want to have a mistake. I'll just give you some antibiotics just in case. That has to stop. This really has to stop because what we need is better diagnostic medicine. What we need are the nerds in the microbiology lab to figure out what's wrong with you and say definitively, yes, you have a cold, you have COVID, you have the flu, you have RSV, you have whatever, you have strep throat, you have a bacterial infection, and then only reserve those antibiotics for the people who actually need them. And do they need them? Yeah, sometimes they really do. Antibiotics can save your life. But because they're so cheap and easy, and I'm not going to lie, there are patients who demand a prescription. It's some kind of weird, mentality that patients have. They're like, well, I'm not leaving until I have pills because the pills are going to make me better. And they don't necessarily even understand the connection to all of this stuff. Here's a really good, easy way to throw out a whole bunch of antibiotics. Don't give them to animals, right? Don't pump chickens and cows and pigs full of antibiotics so that they're basically a source of resistant bacteria. Now, the problem with that dilemma is we should expect more foodborne illness. And people don't want to have diarrhea after they go out to eat. I get that. I totally do. But maybe we just need to normalize how we raise our animals for meat and egg consumption so that they're healthier and happier animals, are getting lots of exercise and lots of fresh sunlight and, vegetables. Like there's just a better way to do this. And that doesn't mean farming them in a big barn that's just so crowded and full of feces and pathogens that they need antibiotics to even survive. I will also say this one last thing. Antibiotics make animals fat. And so if there's an incentive for a rancher or a farmer to have a bigger, fatter, heavier animal because they're getting more money for it, maybe we should rethink how we monetize our animal husbandry industry. Failure to take the full dose of antibiotics. You know about that death curve. You know that if you don't go all the way to the end, you still have a few survivors on there. And the problem is a lot of people take the pills until they feel better and not necessarily until the end of the death curve. I've already mentioned that I think maybe antibiotics are too cheap and we need to maybe refrain from giving them away. Maybe they should be for special occasions, and those special occasions are when they really are mattering to a patient. And educating patients. That's going to be the hardest thing. Patients really can get very stubborn. Now, some good news, we can mix and match different compounds. Maybe we take 2 old antibiotics that by themselves are not as effective, but we put them together and we actually see something called synergy, which is that they work better together. That's cool. Another problem, though, is the reverse of that, which is antagonism. That's something that we want to avoid. And, looking at drug interactions that could cause antagonism is something that basically you learn how to do in pharmacy school. So some things we might actually benefit from tinkering around in the lab and adding a little of this, a little of that. We're actually adding trace amounts of silver to antibiotics, like a very, very small amount of silver, but we're trying other strategies that are, not even other drugs. They're just other substances that might give our arsenal some new life. Okay, I thought I'd talk a little bit about vaccines. And before I talk about vaccines, I just kind of want to give you a little bit of my perspective about vaccines. I will say that vaccines, they really have a lot of misinformation associated with them. And I think it's because we have a lot of medical conditions that are really scary now. Their causes are not necessarily understood. Sometimes they happen around the same time as early childhood vaccines occur. And the science of vaccines is actually extremely complicated. So a lot of times people don't generally understand how vaccines work. And there's, this birth of social media information where people sort of surround themselves with kind of what they want to hear. And, it's really interesting to see how this has unfolded in the last few years. And it's not just from the COVID vaccine, which definitely got a lot of craziness associated with it, but from really the association of vaccines to autism, that's kind of where this really started, and it's really snowballed in a way that has a lot of really concerning impacts on just the overall health and how people are going to move forward out of a pandemic, or maybe keep from getting other severe, illnesses. But I will say we want easy answers. It's human nature to want easy answers, and this is poison, this is bad. That's a really easy answer. I think the harder question is understanding our relationship to a very large planet with problems. There's going to be displacement of plants and animals and climate change and diseases that are coming from places where we haven't interacted with them before, that, like COVID, for example. We'd never really seen this virus before. We didn't have any immunity to it. We didn't have any way of, learning to live with this virus. It kind of hit us with a slam dunk. And then, you all saw how that kind of panned out. And we're really lucky that COVID sort of evolved into more of a seasonal cold, at least for most populations. It was really scary there in the beginning, though. And the fact that we have a vaccine or a bunch of vaccines is sort of like one of the triumphs of science, I have to say. It was like a triumph. And it was sad for me when that just turned into a conspiracy theory. Anyway, let's talk about like vaccines. We've got classical vaccines where we basically train your immune system with a piece of a virus, or maybe even a knockdown, like sort of degraded but still a little bit alive, but mostly so weak that it can't cause any problems virus. Maybe even just a piece of a microbe. We can train it up to do that. But basically, we're just telling the immune system to do what it does best, which is recognize things, and then it has the information that it needs to attack. So, like I said, we could use a shell. We could use a weakened version of a microbe. We can even use a chemical toxin to train your immune system once we've made it inert. And these are all things that basically allows your immune system to just do what it does. It just finds it. It learns how to neutralize it, and then you don't get sick, which is awesome. We do have some new vaccines. Adjuvant or conjugate vaccines are even more specific. These use just a tiny little reactive molecule, like maybe a tip of something from a microbe to basically train your immune system, and you can get a very good antibody production match. DNA vaccines, these are really interesting. DNA vaccines are to basically train your body to recognize when there is a mutation in your own body, for example, cancer. So if you could use your immune system to identify those abnormal cells, maybe at the very beginning before they get really bad, we would basically prevent cancer from happening, which is huge. We can also, after someone has cancer, give them immune therapy, which is like basically a DNA vaccine, where we can try to retrain their immune system to help find and neutralize those same tumors. It doesn't work as well when it's already advanced cancer, but sometimes it is the only thing that will work. And I gotta tell you, there's some really exciting stuff they're doing with lung cancer, stage 4, which would have been a death sentence. We can actually do immunotherapy to at least extend life, but sometimes put people into remission. And then, of course, the mRNA vaccines. The mRNA vaccines were originally developed as a cancer vaccine, but for sure can be used in other ways, such as with COVID. And the idea of an mRNA vaccine is that it's surrounded by a lipid nanoparticle that is basically going to import into your cell a little piece of RNA, which is then going to be used as a transcript to produce whatever that little transcript is for the COVID vaccines. It was the viral spike. And then when you make this spike, your immune system is going to recognize that and then make a huge antibody reaction to it, much stronger than the classic vaccine methods where it was just inert and there was just a little bit of it that was injected into you. This is like a larger response, so you get bigger immunity and then neutralize that pathogen when you come into contact with it. Now, there's a lot of different brands of the mRNA vaccine out there, but I will say they all sort of work based on that principle. And while COVID is probably the most familiar to you, we will probably be seeing influenza vaccines have an mRNA option. I guess you could still use, the flu vaccine that's grown in an egg and all that kind of stuff, like if that is your preference. But the nice thing about the messenger RNA is we can actually use a piece of the influenza virus that is universal for all flu strains. And this could actually stop the flu. This could be the answer for how we stop flu, because there's so many different versions of the flu that we can't possibly have that many flu vaccines. We need something different. Other exciting possibilities, this could absolutely be a cancer vaccine. And we are really studying the long-term efficacy. One of the things we have discovered is the messenger RNA vaccines seem to maybe elicit antibody production for a shorter period of time than forever. Maybe you do have some immunity for years, but like we're just kind of learning about this new technology since we've deployed it on such a large scale. It's kind of an interesting question. Well, how long does that really good immunity last, or does it maybe last forever but taper? I don't know. We'll see. Here's a question that you might have. How did we come up with the COVID vaccine so fast? And is it dangerous because we like skipped a bunch of steps or something? And what I'll say is a lot of the red tape was actually completely eliminated. And that's actually super important because when you do biomedical research, it's usually the grant applications and the safety guidelines and all this kind of stuff. It takes forever to just do the paperwork. So they basically took that step away. They purchased the doses before we actually produced the doses. The government actually put up the money so that there was no risk for the pharmaceutical companies. And that's actually something that is a big concern. We know that in our system of healthcare, our pharmaceutical companies are for profit. They want to make money. So they don't want to like develop a drug that nobody's going to buy, like for billions of dollars. They would go out of business. So when the government did that, they're like, look, even if this doesn't work, we're just going to give you the money and then we'll see what works and then we'll buy those. But you're not going to lose any money, which was kind of like novel. Like the government never does that kind of stuff. Also, the government built these huge scaling facilities so that the biopharmaceutical companies, once they had a drug that had been proven safe and that was going to work, they could basically use these big factories that had just been built at no cost. So that was a huge incentive for basically all pharmaceutical companies to get into the game. And I'll say this. We needed volunteers who would actually test this vaccine. And I mean, that's probably the scariest thing to do is take a vaccine that's only been tested in like animal trials and stuff like that. But, you know, this isn't technology that was brand new. This is technology we've been working on for 20 years. We had done some small scale studies. And when we were scaling it up and we wanted to see like, well, was it working in all age groups and, you know, all ethnic groups, all of that information we need. The volunteers who wanted to be part of this trial, there were so many volunteers that the pharmaceutical companies had to turn people away, which is nothing that we've ever seen has been like that. When COVID was killing people, and we had no choice but to sort of stay in our houses and, you know, essential workers had to go to work to kind of keep the world moving. When that was happening, people were like, I will do whatever I can to see that my kids have a chance, you know, to come back to life and go back to school and all of that stuff. Thousands of people would line up and they basically said, test me. I want to help. I'll do whatever I can. And that was kind of amazing. And, you know, now we have a lot of options and there are actually people who don't want to believe in the science of this vaccine. And that is such a gift that the world gave us. Right? Like the people like all got together and like fixed this problem. And now there's enough immunity from vaccines and natural acquired COVID infections and that kind of stuff that it's not the worry that it was before. But man, what an amazing accomplishment for science and society. And it wasn't just America. It was like all around the world. Like everybody was just like, what can I do? Like, what can I do to help? And we kind of got through it. It was still a trauma, but we did it. A couple of other interesting things, just so you're not too sad about the future. We are looking at some new developing drugs. And these are still years away, but I think they're very exciting. We're also looking at antimicrobial peptides, things from plants and animals. And, you know, we have a lot we can learn from nature. And sometimes it's the simplest things like watching what a sick animal eats. Why do they choose that grass or that flower? And then you go to that flower and you're like, oh, wow, there's something really antimicrobial and special here. Antisense agents, these are things like AZT. We use it for disrupting viral replication. Basically, how can we treat HIV right now? We can give it a a false molecule and that assembles into its DNA and it doesn't work right and is broken. It's very cool technology. I'm also very excited about bacteriophages. Phages can be used as basically a systemic therapy. I know it feels weird to think that we would inject like a virus to treat someone's bacterial infection, but it actually works. And before we had antibiotics, this was actually a very innovative therapy. It was much more popular in Eastern Europe and Russia. Actually, Ukraine had a huge biomedical research center for phage therapy, and they had viruses that would treat pretty much every type of diarrhea, like cholera or giardia. They would use phages to basically do what those phages do, which is attack that specific host. And it's novel here, but it could be a really interesting approach. I think that there is some real value in looking at some of that old bacteriophage science and maybe seeing if we can use it once again. Draco is a very new antimicrobial therapy that basically causes infected cells to initiate apoptosis, which is cell suicide. Usually cells that are damaged or disabled have this program in them that's like, oh no, I'm in distress, I'm not going to make it, I'm just going to go ahead and blow myself up. Well, sometimes that program gets dismantled by an infection, and that's bad because then you have a very abnormal, unhealthy cell. So it's interesting to me that we have a therapy that basically goes in and says, I don't care what's wrong with you. You could have a variety of illnesses. Just kill yourself right now, and then we'll stop worrying about it. And it actually works. And this could actually be a universal viral-like therapy, but it's still very, very, very much in the research stage. Other exciting possibilities, there are some peptides in alligator blood, frog skin, that are just antimicrobial, and they're specifically good for things like MRSA. So that might be very helpful. Cholesterol drugs, one of the things we've learned is that when people have lower cholesterol, they have lower blood infections. And so this is interesting. It's not always easy to take all the cholesterol out of someone in the ICU, but it's actually something that might be sort of a bedside therapeutic option for some infections or people who are prone to infections, I guess. And like I mentioned, I just think animals have a lot to teach us. I think we just need to study how they survive. Like, what do they do? What do they eat? And are there chemicals that we can also look at? In terms of physical things, we're looking at surfaces like shark skin that just naturally repels bacteria and creating that in a nanopolymer. So this is our version of shark skin that we make out of nanotechnology on the top, and the shark skin is on the bottom. Not the same, but it has the same effect, which is that it repels bacteria. And if we could have surgical instrumentation, bandages, things that are semi-critical or critical that repel bacteria, that would be awesome. Other things, I read some interesting articles a couple summers ago about how gecko skin and cicada wings actually can puncture bacteria, which I think is really interesting. It's sort of like shark skin. It's just another thing that we might actually look at moving into some of our surfaces or even instrumentation. Other things, I'm always very open to essential oils, very potent plant-based antimicrobial chemical, quorum sensing interference. Remember, these microbes are communicating with one another electrically, and if we can interfere with how they coordinate signals for, say, releasing toxins, could buy us some time. Certainly not like an antibiotic, like killing like level option, but sometimes time is what you need to reconfigure your approach. We have some drugs that will actually concentrate in the blood rather than in the digestive tract where it is swallowed, which is kind of cool. I think I mentioned we're adding silver to things, which I just think is so funny because it's like the literal silver bullet, right? Like I'm just like why has silver always had this history of like fighting bad things like diseases or vampires or whatever? I just find it so fascinating that silver has a special property that people have always identified, and now it's like this medical like literal savior. And anyway, we do have some peptides that can penetrate biofilms, which is super important because biofilms will basically keep all the drugs from penetrating. SNAPs, another kind of cool thing. These are like little, I think of them as like little ninja stars. Like they just get thrown at bacteria and they're so sharp they shred everything in their path. And this is also very much in vitro. So this is in the petri dish stage of development. But if we could like physically attack resistant bacteria, they can't form resistance to a physical attack. They form resistance to chemicals. So this is just a very, very different approach. And this is kind of the big picture where I want you to ponder things. We're now in a post-antibiotic era. Our last drugs are becoming ineffective. And, because we've been so focused on COVID for the last years, we're behind the 8 ball here, where now little things can be life-threatening emergencies. And just know, we always have to give antibiotics when we do surgery. Imagine life if surgery becomes a dirty procedure and we can't keep you from getting a nosocomial infection, which will kill you, right? It's terrible. Do we need to invest in new drugs? Yeah, of course we do. But we have that model already. Throwing money at pharmaceutical companies isn't necessarily a solution because there is money, right? So it's not just the money. They want drugs that you take forever. They want the Lipitors or the Prozacs where, you get a pill and you take that pill forever. That's how they make a lot of money. We need another approach. But should we keep investing in drugs? Of course we should. Should we look at herbal remedies? I think so. Some of them are garbage, for real. Some of them might actually have some value. Maybe we need to take that seriously and take them into the biochemistry lab, understand those mechanisms, and then maybe harness that power. Maybe we can make it more potent. I want you to think about this question. This is the most important question of the chapter. How do we deal with this problem? And it is a problem. I just think, out of the box creative ideas are what we need. The standard make the drug companies do it. That's only gotten us in the situation that we're in for, the last years. So really sleep on it. I think it's a good question for everybody in modern society to ponder.